video, we're going to look at how to draw a Bohr diagram. So Bohr diagrams, though they use an outdated model, so we have come a little bit further in our understanding of the atom since Bohr's planetary model, it's a really good tool to kind of diagram out the electrons in different energy levels so we can start to view the valence electrons and put our focus on that. And the valence electrons will give us some information about how likely an element is to form a compound or bond with another element. The valence electrons are the outermost electrons, or the electrons in the energy level or electron shell that's furthest from the nucleus. And you might hear me use the term electron shell, or you might hear me use the term energy level, and those terms are interchangeable. So when you're doing a Bohr diagram, okay, you would put protons and neutrons in the nucleus because that's where they're located. Sometimes you'll see an N to abbreviate for neutrons, a P to abbreviate for protons. Some people enclose the nucleus with a circle, some people don't. It's completely up to you. Then you put in your electrons outside of the nucleus into energy levels. You have to fill the first energy level or the first shell before moving on to the next. So the first energy level, which is closest to the nucleus, can hold a maximum of 2 electrons. Maximum meaning it can hold 0, 1, or 2 electrons. Once you fill that, you'd have to move to a second energy level, which is a little bit further from the nucleus and requires more energy for those electrons to occupy it, and that's why it's filled second. So the second energy level can hold a maximum of 8 electrons. Once that's filled, you can move on to the third, which can hold 18, and then the fourth, which can hold 32. And there's a little bit of, once you get past the second energy level, there's a little bit of, if you get to our current model, which is the wave mechanical, there's a little bit of difference of how these electrons are actually filled. The third level doesn't fill completely before the fourth starts, but that's something that we'll look at further once we get to a whole chapter on electrons. So we're really only going to get to the third energy level, the beginning of it, so this will hold true. So keep track of how many electrons you put in each energy level because the total number of electrons should add up to the total number of electrons that atom or ion should have. So let's look at an example. Let's say I give you C12. And I ask you to draw a Bohr diagram, and let's say we're going to choose the most common, so here I gave you the most common isotope, C12. You'll notice that the 12 is closest to the atomic mass, but when you're doing this, remember to look at the mass number that's given in the problem. So if this was C12, I would use the fact that the protons and neutrons add up to 12. If this was C13, then I would use the fact that the protons and neutrons add up to 13, and I would subtract to find neutrons. You never use the atomic mass, which is in the periodic table, to find the number of neutrons. You want to look at what is specific to the atom that's given to you. The atomic mass is just an average of all possible mass numbers for that particular element. So the neutrons, I would subtract 12 minus 6, I'd get 6 neutrons. And since this is an atom with no charge, the electrons would be equal to the number of protons. So when you're thinking about drawing your Bohr diagram, and you'll see how I put these guiding questions to kind of think about how many energy levels or electron shells you're going to need. So if I have 6 electrons total, and I know only 2 can fit into the first, that means I'm going to have 2 in the first and then 4 in the second. So I'm going to have 2 electron shells. My outermost shell would be the second energy level, or the second shell, and the electrons that are in that second shell would be called valence electrons. So it's going to end up having 4 valence electrons. So my Bohr diagram might look something like this. I have the protons and neutrons in the nucleus. If you want to enclose that in a circle or not is up to you. I have the first energy level closest, which holds a maximum of 2, and then I have 4 more electrons I need to add up to 6, so I put those 4 in an outside shell. Some people tend to group their electrons into pairs, and that's completely fine too. I don't care which way you do at this moment. And that would be carbon 12. Instead, so as you get further and further into adding more and more electrons, sometimes it gets tiring to have to draw these electrons as dots or circles. So another way of doing this is instead of drawing the dots or circles for electrons, you can literally just put the number of electrons that are in that shell kind of in that energy level or in that circle or orbit. So I would say there's 2 electrons in the first energy level and 4 in the second, and this kind of allows me to see, oh, there's 4 valence electrons, 4 electrons in my outermost or my last energy level or electron shell. So I kind of like the numbers better, but you can feel free to do either or. Notice in this one I enclosed the protons protons and neutrons in a nucleus, but you can do it without doing that too. So take a moment, try this example, pause the video, then give it a shot. I put kind of some guiding questions to help you draw it. So always think about the number of subatomic particles. Li has an atomic number of 3 if I were to look it up. So there's 3 protons. 7 minus 3 gives me 4 neutrons. And the electrons would be the same as protons. Since this is an atom, there would be 3. Since there's 3 electrons, only 2 can fit in the first, 1 can fit in the second. So it would look something like this. Or if you want to write them with numbers, 2 electrons in the first, 1 in the second, 2 plus 1, add up to 3 electrons. This has 2 electron shells or energy levels, and it has 1 valence electron in its outermost shell, which is the second shell. So basically the second shell is the valence shell. Take a moment, try this example, then pause the video. Okay, how many protons? If I look up sulfur, it has an atomic number of 16, so there's 16 protons. 32, the mass number, minus 16 gives me 16 neutrons, and since this is neutral, there's also 16 electrons. So if I'm going to draw this, okay, I put the protons and neutrons in the middle, and then I start divvying up my electrons into energy levels. And again, sometimes it's easier than looking at all these dots. It's kind of easier to write it with numbers. So I know 2 maximum can fit in the first shell. Okay, so I've used up 2. I know 8 maximum can fit in the second shell. 2 plus 8 is 10. I have 6 more to go to add up to 16, so I put those 6 in the third shell, which can hold up to 18, so those 6 are fine. And I notice that I have 3 shells, 1, 2, 3, and that's why I have 3 numbers here. It tells me how many electrons are in each of the shells, 2 in the first, 8 in the second, 6 in the third, and it has 6 valence electrons. So what you'll notice is this is an easy way to kind of start seeing what we call the electron configuration, how electrons are arranged into shells or energy levels in the atom, and it lets us see the valence electrons easily so we can predict reactivity and how many electrons this might gain or lose in the future. So if I wanted to do an ion, I can do the exact same way. Just remember that ions might gain or lose electrons, so the number of electrons are no longer equal to the number of protons. So if I wanted to take this and do S2 minus, let's say, and this is just sulfurs from before, just carried over. So S2 minus have the same number of protons, it's still sulfur, so it's still 16. Same number of neutrons, it still has the same mass number, 32 minus 16 is 16, but the 2 minus charge tells me it's gained 2 electrons. It has 2 more electrons than protons, and that's what gives it this 2 minus charge, because electrons are negative. There's 2 more electrons than protons, and it's outnumbered. So the atom would have 16 electrons, but the 2 minus tells me it gained 2 more, and it has 18 electrons total. So I need to add 2 more electrons to my structure. Where do I want to add them? I can't add them in the first. I can't add them in the second. I've got to add it to my outermost energy level, which can still hold more. So here's 1, here's 2 more. Again, you can keep these in pairs if you'd like or not. Or if I wanted to do it with the numbers, it's 2, 8, and it used to be 6 if it was the atom, but it now has 2 more valence electrons. It now has 8. So notice it still has 3 shells, but it now has changed the number of valence electrons. There are 8. And notice that this now has the same number of electrons, 2 plus 8 plus 8, 18, which adds up to 18, as the nearest noble gas to sulfur, which is argon. And what we notice is that main group elements tend to gain or lose electrons in order to have the same number of electrons as the nearest noble gas, because it's more stable. It doesn't become the noble gas because it still has 16 protons. It doesn't have 18 like argon, but it has the same number of electrons. Take a moment, try this example, pause the video, check your work. Sodium 23. Sodium has 11 protons. 23 minus 11 is 12 neutrons. That's neutral. I don't see any indication of charge, so it has 11 electrons. And I would put the protons and neutrons in the nucleus. 2 can go in the, and I'll show it this way, 2 can go in the first energy level. 8 can go in the second. 2 plus 8 is 10. I have 1 more, and I'll put that in the third energy level. So there's 1, 2, 3 energy levels. My outermost energy level, the third energy level, holds 1 electron. We call those the valence electrons. Instead of the atom, you might be asked for the ion. Take a moment, try that, and this is just the atom carried over. Okay, same number of protons, 11, because it's sodium. Same number of neutrons, because it has the same mass number. 23 minus 11 is 12. But I have a 1 plus charge, so I have 1 more proton than I do electron. Essentially, I have lost an electron because electrons are negative, and that's why the protons now outnumber them, giving it a net positive charge. So if I would have had 11 protons in the atom, this ion has lost 1. It now has 10. So I can take this electron away. I always want to take it from the outermost energy level so that the maximum of the first and the second are still there. So notice that actually when these electrons are going to lose, or when these atoms are going to lose electrons to form ions, they're actually going to get smaller in size. And I could have written it this way too, 2, 8, and I got rid of the 1. If you wanted to leave the outer shell and write a 0, that would have been correct too. It has, but it actually has 2 shells now that are filled. The third is no longer filled, and it now has 8 valence electrons. We don't like to say something has 0 valence electrons. We want to see out of the shells that are filled, how many are in your outermost.